Okay, so we have seen in the previous video, we have defined polynomial rings over commutative rings with unit element, and this is a generalization of polynomial rings over a field. And we saw in particular this result, that if R is an integral domain with unit element, then the polynomial ring Rx is also an integral domain with unit element. And this naturally led to the corollary that if instead of, in place of only one variable or one indeterminate, you have any finite number of indeterminates, then this is also an integral domain with unit element. And then once we had that, we can of course consider the special case where in place of R you have a field F, because every field is also an integral domain with unit element. So this is again an integral domain with unit element, and being an integral domain, it has its own field of quotients, which we call the field of rational functions in these variables over F, and which we denoted by this notation or this symbol. Okay, now let us further our study. Let's bring in new concepts and see what we can do in this with these very general polynomial rings. So we start like this. Exactly as we did with Euclidean rings, one can speak of divisibility, units, etc. in an arbitrary integral domain with unit element. So in the section where we developed the theory of Euclidean rings, there we saw that by definition a Euclidean ring is an integral domain. And then after, in the course of developing the theory, we also saw that every Euclidean ring has a unit element. So instead of considering Euclidean rings, we can much more generally consider integral domains with unit element. And you also recall that we defined these concepts of divisibility, units, primes, etc. in a Euclidean ring. So such things can also be done in this more general setting of an integral domain with unit element. So that's what we are going to do, and we will see how far we can go with that. So let R be an integral domain with unit element. Two elements A and B in R are said to be associates if A equals UB for some unit U in R. like that. So you can see that two elements being associates, this is the same definition that we had there also for a Euclidean ring. So the only difference that we will see with these definitions and the ones we previously got is that the background ring now is not necessarily a Euclidean ring. It's in general an integral domain with unit element. A non-zero non-unit A in R is said to be an irreducible element or a prime element if whenever A equals BC, where B and C are in R, then exactly one of B or C is a unit in R. So that means if you have a non-zero non-unit element in our integral domain R, such that whenever you have a factorization of A as a product of two elements B and C from R, then exactly one of them has to be a unit. In other words, an irreducible element is an element which has no non-trivial factorization. For example, in our familiar integral domain of integers, you know that 2 is a prime element, because in the possible factorizations of 2 as a product of two integers, you see that in each one of them exactly one of the factors is a unit. In these first two cases, that unit is 1. In the second two cases, the unit is -1. So which has no non-trivial factorization. In the ring. In the ring is important because, for example, one may try to say that this is a non-trivial factorization of 2. Yes, it is a factorization of 2, but not in the ring of integers. It's in the ring, or rather in the field of rational numbers. There it's a factorization. So the background ring matters. Okay, now we come to a definition. Definition of a unique factorization domain. An integral domain R with unit element is said to be a unique factorization domain, UFD in short, if there are two conditions: every non-zero element in R is either a unit or can be written as a product of finitely many irreducible elements of R. Let's call this A. This is the first condition, that every non-zero element is either a unit or is factorizable as a product of irreducible elements of R. And the second condition is that this decomposition is unique in a sense. The decomposition of a non-zero non-unit element in R as a product of finitely many irreducible elements of R as stated in A is unique except for order and associates of the irreducible elements involved. So what this definition says, it says that an integral domain with a unit element is said to be a unique factorization domain if for a non-zero non-unit element factorization is possible as a product of finitely many irreducible or prime elements, and this factorization is unique except for the order of the factors. You can change the order of the factors, and for the associates, that is, let me again bring that example back. 2 can be written as a product of prime elements in only this way, because 2 itself is a prime, or let's take a non-trivial example. Let us take 6. Now 6 can be written as 2 times 3. Okay, so these prime elements or these irreducible elements in the integral domain of integers are appearing in the factorization of 6. And note that 6 is neither equal to 0 and nor equal to a unit, because the units in Z are 1 and minus 1. Now you can change the order. In place of 2 times 3, you can write 3 times 2. That you can do, or you can replace the any one of the prime elements or both of them by its associate. And how do you get an associate of a prime element? By multiplying by a unit. You can write, for example, minus 2 times minus 3. These are also prime elements, and they are obtained from the other prime elements by multiplying by the unit minus 1. So that way you can have different looking factorizations. But if you really think about it, these are not considered to be that different. I mean, they are just associates. You are not getting any new prime element in the factorization of 6. That is not possible. So by uniqueness we mean this kind of uniqueness. So that's why we have said the decomposition of a non-zero non-unit element in R as a product of finitely many irreducible or prime elements of R as stated in A is unique except for order and associates of irreducible elements involved. So that's the definition of a UFD, a unique factorization domain. Okay. Now if you go back to the theory of Euclidean rings, theorem 372 asserts that every Euclidean ring is a unique factorization domain. But the converse is not true. For a field the ring the polynomial ring over F in two variables x1 and x2. Is not a principal ideal ring. And the fact that this is not a principal ideal ring, we will prove in the exercises, that every ideal here is not a principal ideal. There exist ideals which are not generated by a single polynomial, and hence cannot be a Euclidean ring. because we have seen in the theory of Euclidean rings that every Euclidean ring is a principal ideal ring. So since it's not a principal ideal ring, so this cannot be a Euclidean ring. However, we shall see that, let me write it in the next line. This is a unique factorization domain. So this provides us with an example of a unique factorization domain that is not a Euclidean ring and that is also not a principal ideal ring. In general commutative rings, we can speak of greatest common divisors of elements. However, the problem is that they may not exist. But in a unique factorization domain, two elements at least one of which is non-zero are guaranteed to have a greatest common divisor. That means if you are in a general commutative ring, then you can define GCD of two elements, but may not exist even when both of them are non-zero. But if you are in a unique factorization domain, then they will exist. Recall that in a Euclidean ring we already proved that they exist, and Euclidean rings in particular are unique factorization domains that we proved in the theory of Euclidean rings. But here, for example, this is a unique factorization domain which is not a Euclidean ring. However, here also GCDs exist, a greatest common divisor, and we will prove that in this section in the exercises, and we have these results also regarding GCD. Lemma 3.11.2. if R is a unique factorization domain, and A and B are in R, not both 0, it's basically this thing. Then A and B have a greatest common divisor. We are keeping the same notation for GCD of elements from such a general system, a unique factorization domain. The same notation that we also had in the ring of integers. Like for example, the GCD of 2 and 3 is 1, and this is the notation that denotes the GCD of 2 and 3. So the same notation we have kept here also. In R, this is also an element in R. Moreover, if A and B are relatively prime, that is, one is a GCD of A and B, where one is of course the unit element in R, and A divides BC where C belongs to R, then A divides C. So you see that not only are the concepts similar or almost the same in this setup, also the results are also the same. We will prove these things in the exercises, and there is this very important corollary. If A belonging to R is an irreducible element, in this context R of course is a unique factorization domain in R, and A divides BC, then A divides either A divides B or A divides C. You may be getting some noise contamination or some background noises. Please ignore them. Some festival is going on outside, so that's why. Okay. So we have seen these things. Now what? Now we wish to transfer an analog of Gauss lemma that we had in the ring of integers along with the field of rational numbers in our setup. We now wish to transfer An appropriate version of Gauss lemma, which is, it was called lemma, but it was a theorem. Yes. Which we proved for polynomials with integer coefficients to the ring Rx, where R is a unique factorization domain. Let me feed this some ink first. Okay, now before we do that, we also have to define those things that we needed in Gauss lemma, namely content of a polynomial, primitive polynomials, that we defined in the context of integer polynomials. Now we have to do those same things for polynomials in Rx, where R is a unique factorization domain. So let's do that. Given a polynomial a0 plus a1x etc. plus amx to the power m in Rx, the content of fx is, definition is same, is defined to be we cannot write the a greatest common divisor of the coefficients Note that because in UFDs GCDs exist, that's why this definition is significant. Otherwise the definition would be hollow or vacuous. I mean, we may not be able to say vacuous, but frequently we will come across situations where GCD does not exist or content does not exist, even when all the coefficients are non-zero. So that will happen if you are working in a general commutative ring. But now our commutative ring in particular is a unique factorization domain. So there the nature of GCD is just like the nature of GCD in a Euclidean ring. So we will continue to have all the things, or more concretely, just like the nature of GCD in our familiar ring of integers. So if you get one GCD, then you will get other GCDs also, because all the GCDs are associates. By multiplying by units, the content of a polynomial is unique up to associates. We denote the content of fx by cf, c of f, that is content of f. Now the other things are also going to come similarly. A polynomial fx in Rx is said to be primitive if Cf is equal to 1, or equivalently if Cf is a unit in R. Then what else is true when we have these concepts, that if you multiply two primitive polynomials you will get a primitive polynomial. So those things are true, and we however we need to prove them, but these things the proofs we will do in the exercises. Given any polynomial fx in Rx, one can write fx equal to a times f1 x, where a is the content of f and f1x is a primitive polynomial in Rx. We need to prove this, we will do that. And this factorization is also unique except for multiplication by units of R, that means up to associates, they are the same. That means this decomposition. The above decomposition of fx as a product of an element of R and a primitive polynomial in Rx is unique. This uniqueness also we will have to prove. Okay. Now we are going to state the version of lemma 3.10.1. Okay, and its proof goes over completely to our situation, and that means we can just copy and paste the proof that we previously had in the previous section of lemma 3.10.1. In our case, that same proof will work. The only thing is that there in the proof we had one prime number p. It has to be replaced by a prime or irreducible element in our case. That is the only difference. So we will write like this. The proof of lemma 3.10.1 goes over completely to our present situation. The only difference is that the prime number p, you visit the proof, you go back to that proof and you see that there you have a prime number p, has to be replaced by a prime element of R, and this is the statement. If R is a unique factorization domain, then the product of two primitive polynomials is again a primitive polynomial in Rx. Okay, so you actually do go back to the proof and see that whatever the author is saying is true, indeed true, that the same proof works in this case. The only difference is that the prime number p has to be replaced by a prime element from our unique factorization domain R. There you had, in place of R, there you had the ring of integers. So that is the difference. Okay, now given fx and gx, two polynomials in Rx where R is a unique factorization domain, we can write fx as a times f1x and gx as b times g1x, where a is content of f, b is content of g, and f1x and g1x are primitive polynomials in Rx. Now, by this lemma, the product of these two polynomials is also primitive. So, implies that the content of fx times gx is AB, and this equality, we can draw this conclusion from the fact that the product of such a polynomial as its what I am saying is that the factorization of such a polynomial as a product of its content and another primitive polynomial is unique, essentially unique, except for multiplying the content by a unit from the unifactorization domain. So it's because of that uniqueness we are getting the fact that the content of this has to also be equal to AB. That is, content of Fg is equal to content of F times content of G. Note that the uniqueness of this type of factorization is not absolute in the sense that yes, this will be the content, and this will be the primitive polynomial. It's up to associates, up to multiplication by units. So you have to understand that this equation is not literally an equation in the ordinary sense. It just says that if CF is one content of F and CG is one content of G, then their product is one content of FG. Why do I say one content? It's because if you have a polynomial that has a content, say GCD of the coefficients exists, then you can change the GCD also. It's not necessarily only one GCD. You will get other GCDs if you multiply the current GCD by units. So essentially you actually get, truly speaking, different contents, but they are all associates because the only difference between them is multiplication by a unit. So that's why this is not a single value. This is also not a single value. So this equation is just saying that if you take the product of two contents of these polynomials, then that result is a content of Fg. Okay, so in that sense you have to interpret this equality or equation. So there is a corollary. I mean, we can write this more formally because it's coming from as a consequence of lemma 3.11.3. The fact that f1 g1 is primitive allows us to conclude that AB is also a content of Fg. So that's why this entire conclusion is a corollary to lemma 3.11.3. If R is the unique factorization domain and if fx and gx are two elements in the polynomial ring Rx, then up to associates. Up to associates is there, which just simply says how this equation is to be interpreted. And we can clearly extend this to a product of any finite number of polynomials by a simple induction. One can extend this result to the product of finitely many polynomials in Rx. That is, if say f1, f2, f3 up to fn, these are polynomials in Rx, then you have this. There are other results also in this section. We will do that in another video. We will ultimately see that if R is a, so far we have seen what? if R is an integral domain, then Rx is also an integral domain, and hence the multivariate polynomial ring is also an integral domain. Now we will show after this that if R is a unique factorization domain, then Rx is also a unique factorization domain, and hence this will be a unique factorization domain. And then in place of R we will consider a field, and thereby we will get the fact that this is a unique factorization domain ultimately. Okay, so we will do this, we will see those things in the next video. So I end the video here itself. If you have any doubt regarding these things, then you can comment in the comment section. So that will be all for tonight in ring theory. So this is me signing off, Lucifer from A Mathematical Room. Have a nice night.